The Earth's rotation forces all stars in the sky to rise and set daily. However, depending on latitude, some celestial bodies never drop below the horizon line. At the geographic pole itself, all visible stars move strictly parallel to the mathematical horizon. The moment a celestial body reaches its highest point is beautifully called upper culmination.
Have you ever just looked up at the night sky and wondered about that slow, predictable parade of stars? It's like a grand celestial waltz, right? Well, today, we're going to dissect the beautiful geometry behind that very motion. We'll get to the bottom of why the stars, the sun, and the moon all trace these specific paths across our sky. All right, so to really get a grip on this, we need to start with a foundational concept, the celestial sphere. I want you to picture this. Imagine the Earth, our little vantage point, is sitting dead center inside a colossal imaginary sphere, and all the celestial objects we see, every star, every planet, are projected onto the inner surface of this sphere. Now, of course, it's not a real physical object, but as a model, it is absolutely essential. It's the framework that allows astronomers to precisely map the sky and predict celestial movements. So here's our roadmap for this lecture. We're going to kick things off with the daily rotation, the engine behind all this motion. From there, we'll get into the mechanics of rising and setting. Then we'll look at the extremes, stars that don't follow those rules. And we'll wrap up with what's known as culmination, the absolute peak of a star's journey across the sky. Okay, section 1, the daily rotation. At the heart of everything we see in the sky is one simple fact. The Earth spins on its axis. And because we're on this spinning platform, that immense celestial sphere we just imagined appears to rotate around us once every day. This creates a beautiful effect. Every single star seems to trace a perfect circle in the sky, a path we call a diurnal parallel. Imagine thousands of these circles, all parallel to each other, painted across the celestial sphere. Now, let's bring this down to Earth. Literally, we need to introduce your personal point of view, which is defined by your horizon. Just picture the horizon as a great, flat plane that slices right through the celestial sphere. It divides the universe into two halves, the part you can see above you and the part that's hidden below. So what does it mean for a star to rise? It's simply the moment its circular path, its diurnal parallel, crosses that plane, moving from the hidden half into your visible sky. And setting, that's just the opposite, when it crosses back below the horizon. And we need to be very precise with our language here. The point of rise isn't just vaguely in the east. No, it's a mathematically exact point on the horizon where that celestial body first becomes visible. Same for the point of set. It's all about the precise geometric intersection of that star's circular path with the plane of your horizon. This brings us to a really crucial question. Do all stars rise and set for every single observer on Earth? The answer, perhaps surprisingly, is a definitive no. It turns out that whether a star rises and sets for you depends on a combination of two critical variables: the star's fixed position on the celestial sphere and your specific location, your latitude, here on Earth. And of course, there is a mathematical rule that governs this. It all comes down to a relationship between two numbers. The first is the star's declination. You can think of that as its celestial latitude, how far north or south it is on the celestial sphere. The second is your own latitude on Earth. The formula you see here basically says this. For a star to rise and set from your location, its declination must be less than 90 degrees minus your latitude. If it's outside that range, well, something else happens. What's really elegant about this is that a star's declination doesn't just tell you if it rises, but also where. So if a star has a declination of 0, meaning it's right on the celestial equator, it will rise due east and set due west for everyone. But if it has a positive declination, a northern star, it will rise in the northeast and set in the northwest. And conversely, a southern star with a negative declination will rise in the southeast and set in the southwest. It's a beautifully predictable system. All right, so what happens when that formula isn't met? When a star's declination is greater than 90 degrees minus your latitude? Well, that's where we get into the extremes of visibility. We start seeing stars that are either non-setting, meaning they never go below the horizon, or non-rising, meaning they never come up. So, how does this work? Well, imagine a star that's very close to, say, the North Celestial Pole. From your latitude, its entire diurnal parallel, that daily circle it traces, is so high in the sky that the circle never intersects your horizon. It just loops around and around, always visible. The exact same principle holds for a non-rising star. Its daily circle is entirely contained in the part of the celestial sphere that's permanently below your horizon. And this gives us our two categories. A non-setting star is what we call circumpolar. The name says it all. It circles the pole. For anyone in the northern hemisphere, the stars in the Big Dipper or Cassiopeia are classic examples. Then you have the non-rising stars. Their entire diurnal parallel is below your horizon. So for you, they simply don't exist in your sky. You will never ever see them from your current latitude. To really cement this idea, let's consider how your view of the sky fundamentally changes based on your location. We'll take a look at two extreme examples, what you would see if you were standing at the Earth's equator versus what you'd see at the North Pole. The difference is, well, it's night and day. At the equator, your latitude is 0. The celestial poles are sitting right on your north and south horizons. This means that every single star rises and sets. They all travel perpendicular to the horizon and are visible for exactly 12 hours. Over the course of a year, you can see the entire celestial sphere. Now jump to the North Pole, latitude 90 degrees. The North Celestial Pole is now at your zenith, directly overhead. Here, no stars rise or set. All the stars in the northern celestial hemisphere are circumpolar, just making horizontal circles around the sky. And every star in the southern celestial hemisphere, they are all non-rising. You will never see them. A completely different sky. So, what about for most of us living in the mid-latitudes? Well, our sky is a composite. It's a combination of all three phenomena. We have a region of circumpolar, non-setting stars near our celestial pole. We have a huge swath of the sky filled with stars that rise and set every day. And we have a region near the opposite celestial pole of stars that are non-rising, forever hidden from our view. All right, our final section. Let's discuss the apex of a star's daily journey. There's a specific moment when a star reaches its highest altitude in the sky, and this event has a name: culmination. For observational astronomy, this is an absolutely critical moment. To understand culmination, you first need to visualize another imaginary line in the sky. This one is called the celestial meridian. It's a great circle that runs from the due north point on your horizon, passes directly overhead through your zenith, and continues down to the due south point on your horizon. It effectively splits your sky into an eastern half and a western half. Culmination is defined as the precise moment a celestial body crosses this meridian. Now, here's the thing. As a star makes its full 360-degree circle, it will actually cross this meridian twice. The first crossing, the one where it reaches its maximum altitude above the horizon, is called the upper culmination. This is the one we typically notice. But exactly half a rotation later, it crosses the meridian again at its lowest possible altitude, and we call that the lower culmination. And this is where it all connects. As you can see from this table, for a typical rising and setting star, you'll see its upper culmination, but its lower culmination happens while it's below the horizon, so it's invisible. For a non-rising star, well, obviously you see neither. The only case where both culminations are visible is for circumpolar stars. Since their entire path is above the horizon, you can observe them at both their highest and their lowest points as they cross the meridian. So I want to leave you with a question to ponder, to apply these principles. Remember, the sun is just another celestial object, and it obeys these exact same rules. So think about a polar day at the North Pole. The sun has a positive declination during the summer. Knowing what you now know about latitude, declination, and circumpolar motion, what would the sun's path look like? Would it rise and set each day? If you can visualize that, you've grasped the core of everything we've discussed today.
Thank you, friends. Strive for understanding and become wiser. See you soon.